Let's now take up a useful result, and here we are going to consider a maximum for a concave function and a minimum for a convex function. So we are going to take up the analysis for the maximum of a concave function, and the corresponding result applies to the minimum of a convex function. So let's suppose we have a concave function. So we start with a concave function f, and that just means f double prime x is less than equal to 0 for all x in the interval I. That just means if f double prime x is less than equal to 0 for all x in the interval I, we know then that means f prime x is decreasing in I. That means the slope of the tangent to the graph of that function, that slope keeps on decreasing. Now let's suppose that there is an interior point C in I at which f prime C is equal to 0. Let me write that. There is an interior point C in I at which f prime C is equal to 0. I know that f prime is decreasing in I. That means to the left of C, f prime x must be greater than equal to 0, precisely because I know that f prime is decreasing in I. So the slope of tangent to the graph of the function is decreasing in the interval, and there is an interior point C in the interval at which f prime C is equal to 0. At that point the slope is 0. What does that mean? And I also know that slope is decreasing in that interval. That means points to the left of C, the slope would be greater than equal to 0, and points to the right of C, the slope would be, now again I know that the slope is decreasing, so points to the right of C, the slope would be less than equal to 0, precisely because the slope is decreasing in the interval. So if this is the case, given all this, I can now write f prime x greater than equal to 0 to the left of C, f prime x less than equal to 0 to the right of C. This is precisely because of the fact that f prime x is decreasing in the interval. It is decreasing in I, and at C, f prime C is 0. So obviously to the left of it, it will be greater than equal to 0. To the right of it, it will be less than equal to 0, because throughout f prime is decreasing. So at C, f prime is 0. To the left of C, it will be greater than equal to 0. To the right of C, f prime will be less than equal to 0. That means that's just because I know that f prime is decreasing in I. So that just means, before that, if to the left of C, f prime x is greater than equal to 0, and to the right of C, f prime x is less than equal to 0, that just means that the function itself is increasing to the left of C and it is decreasing to the right of C. So from this we conclude that the function itself is increasing to the left of C and decreasing to the right of C. If that is the case, that just means that I can now write hence x is equal to C is a maximum for f in I. And that's a very, very important result. We can have a corresponding result for the minimum of a convex function. So what we are left with then is this very important result that I can write here. Suppose it's exactly what I'm just writing it in a better manner here. Suppose f is a concave function, and I can get to the convex part of it also. It is a concave function in an interval I. If C is a stationary point for f, that means f prime C is equal to 0, that I already know. If C is a stationary point for f in the interior of I, then C is a maximum point, because that's exactly what we have established. We started with the fact that we have a concave function and there is an interior point C in I at which f prime C is equal to 0. That means we have C as a stationary point for f in the interior of I, and we have then established then that means C is the maximum for f in I. So that's exactly what I'm writing now, that if you have you have a concave function f in an interval I, you have C as a stationary point for f in the interior of I, then C is a maximum point for f in I. So in this case, and if I talk about a convex function, then C would be the minimum point. In other words, I can write when C is an interior point of I, then when you have f double prime x less than or equal to 0 for all x belonging to I, and we start with this. You know that C is an interior point of I, and you have f double prime x less than or equal to 0 for all x belonging to I, and f prime C is equal to 0. That just means that x is equal to C is a maximum point for f in I. So we have clearly understood it now, and similarly I can then write Okay, so then this would be the case, and this would be the case, that f double prime x greater than equal to 0 greater than equal to 0 for all x belonging to I, and again the same thing, f prime c is equal to 0. That just means x is equal to c is a minimum point for f in I. Given all this, let's take up a question, and that is this. So we know that the cost of producing q units of a commodity is this. It is aq squared plus bq plus c. And here q is greater than 0. In this case, alright, one very important point, A, B and C are positive. In fact, I should write that these are positive constants. We have to prove that as far as the average cost function is concerned, that has got a minimum at, so I have to prove, the question is, prove that average cost function which is this, it is A of q, it is little a q plus b plus c by q. This has a minimum at q star equal to root c by a. And this is our question. First we have to, so we have to take up the average cost function, and we have to prove that it has got a minimum at q star, which is given to us. So first let me write the average cost function, that is equal to little a q plus b plus c by q. And now I take up the first order derivative, which turns out to be this minus c by q squared. And in this case, if I put it equal to 0, if I set it equal to 0, I get this stationary point, which is a minus c upon q star squared is equal to 0. So that actually gives me c upon, in fact I should just first think of this being put to 0. So you have c by q squared equal to little a, and that means q squared is equal to, so aq squared is equal to c, so q squared is equal to c by a, and q, that is my q star, will be equal to under root c by a. So that is what I get. This is the stationary point of this is a stationary point. In fact, that's the only stationary point of the average cost function. Now we have to obviously prove that this is indeed a minimum point. For that we have to take its second derivative, and its second derivative would be, let me write it here, a double prime q, and second derivative is in fact equal to so the first derivative is this, and actually I can write it as a minus c q raised to the power minus 2. So I can then have it is 2c q raised to the power minus 3, and that means I have 2c by q cubed, which I know is greater than 0 for all q greater than 0, and that just means my a of q, that is convex. So if a double prime q is greater than 0 for all q greater than 0, that just means from here I can say that a of q is convex. And now we can get back to our theorem. What do we have? C is an interior point of I, and we have this f double prime x greater than equal to 0 for all this, and f prime c is equal to 0. That just means that that point is a minimum point. So clearly that's what we see here, and that just means I can now write this implies q star, which is equal to this, is the minimum point. Before we end this section, let's get to that result, that useful result we started out with. Let's just take up that result again. So we know that you have a function which is concave, then you also have a c which is a stationary point for that function in the interior of the domain, and that just means c is a maximum point for f in I. So it's just exactly the same thing. You have f, which is a concave function in the interval I. You have c, which is a stationary point for f in the interior of I. That means f prime c is equal to 0. That just means c is a maximum point for f in I. So that actually is, this diagram is indicative of that point. You see that your function is concave, you have an interior point c at which f prime is equal to 0. That means your c is a stationary point, and clearly you see that it is then therefore a maximum point.